Okay, so before we start, just a reminder that tomorrow is the Chemistry Department Career Pathways virtual meeting on Zoom that we advertised last week, so please try to make it to that. We will also have a quiz on Wednesday. It's been a while since we've had a quiz, so it's time for us to have a quiz. Today we won't finish chapter 24. We'll finish 24 on Wednesday as well as start 25. So the quiz would only go through 23 and then the material that we're covering through today, which is going to be finishing the aldol reaction. We've got three different types or variations of the aldol reaction to talk about today, as well as the Claisen reaction. So we introduced the aldol reaction on Friday. We talked about the mechanism. We talked about the fact that it's an equilibrium process. We talked about that sometimes you can have dehydration, other times you don't. We talked about using heat to promote the dehydration. And we went over the mechanism. Remember, it's a special mechanism for the dehydration, a special type of elimination. So what this graphic here is telling us or teaching us is how to disconnect a target compound into the aldehyde or ketone that would be used to make that target compound via an aldol reaction. And so what we do is we locate the alpha carbon of our carbonyl group, which is going to be here in this one and here in this one. We have two alpha carbons here in the ketone. And so what we need to do is locate the alpha carbon that is either bonded to a carbon with an OH, so that would be this one right here, or the one that's involved in a double bond, which is this one right here. And then in the retrosynthetic direction, we're going to break that carbon-carbon bond between the alpha and beta carbons. So we're going to break this bond. Not this one. This is between an alpha and a beta carbon, but not this one. It's between the alpha and the beta carbon bearing the OH. We break that, and you see that this is the aldehyde, or two molecules of the same aldehyde, that would be used to make this particular aldol product. And then in the case of the enone, or the alpha-beta unsaturated ketone, we break this carbon-carbon double bond, and that leaves us with two molecules of cyclohexanone that would react to make that product. Now with cyclohexanone, would we be able to stop at the beta hydroxy compound? You'll notice that we must have heated it up to generate the alkene, but would the reaction stop at the beta hydroxy compound? Okay, I'll give you a hint. The answer is no. So can you explain why would we not be able to obtain the beta hydroxy compound from a reaction of cyclohexanone? And it has to do with whether or not the aldol equilibrium is thermodynamically favorable. That's something we talked about on Friday. What types of compounds is the aldol reaction thermodynamically favorable for? For aldehydes. Okay, so for ketones, it is not thermodynamically favorable, but our dehydration is irreversible. So if we are performing an aldol reaction with a ketone, if we don't add heat, we're just going to have that starting ketone because the equilibrium is going to favor the starting ketone. But if we heat it up, when we form a small amount of that beta hydroxy ketone at equilibrium, it can undergo the irreversible dehydration or elimination to generate the alpha beta unsaturated compound. So this example also teaches us that it's only with aldehydes that we can generate the beta hydroxy compound, that we can stop here because it's thermodynamically favorable to make that aldehyde. You don't need the dehydration to make it irreversible. But with ketones, you need the dehydration to make it irreversible. And so with ketones, we'd only be able to get the unsaturated compound. Any questions? So the aldol reactions we've talked about so far involve a single aldehyde or ketone making a small amount of an enolate from a single aldehyde or ketone and reacting it with itself to get the aldol product. Could we perform a crossed aldol reaction? Could we take two different aldehydes or ketones and mix them together? We could, but I'll ask you, how many possible products could we get from a crossed aldol reaction? Okay, not only 3, we could get 4 products. This figure here shows us that really nicely. Here we have 2 different aldehydes, which means that we could make 2 different enolates. We see those here. And each of those enolates could react with either of the 2 aldehydes remaining in solution. So you would have 2 different self-aldol products. So this is the enolate from acetaldehyde reacting with acetaldehyde. This is the enolate from propanal reacting with propanal. So these are our 2 self-aldol products. And then we have 2 different crossed aldol products. You might have said 3 because you might have thought, well, there's only going to be 1 crossed aldol product. There's actually 2, because you get a different product when you have 1 enolate reacting with the other carbonyl compound. So this product here formed from the enolate of acetaldehyde and the propanal is different from the product that you get when you react the enolate of propanal with acetaldehyde. You see that these 2 compounds are different. They would be constitutional isomers. They'd have the same molecular formula, but you see that the atoms are connected together in a different fashion. So total of 4 different products obtained from a crossed aldol reaction. So this sums it up very succinctly. It is not synthetically useful, with 2 exceptions. There are 2 cases in which crossed aldol reactions are going to be useful. Okay? The first one is when only one of our carbonyl compounds has alpha hydrogens. Okay? So what kind of carbonyl compounds do not have alpha hydrogens? I'll show you a couple of examples. Benzaldehyde. Are there any alpha hydrogens in benzaldehyde? Okay, there are not. The carbon attached to the carbonyl does not have any hydrogens attached. Formaldehyde. That's another example of a carbonyl compound with no alpha hydrogens. Okay? Can we make enolates from these compounds? We cannot. So if we have this and a carbonyl compound that does have alpha hydrogens, we only have 1 species that can make an enolate. Okay, so that gives us 1 enolate. Now that enolate could react with either of the 2 carbonyl compounds. So to prevent that from happening, we use the carbonyl compound without alpha hydrogens in excess. Okay, so we'll show you an example of how this would work. We'll use benzaldehyde. We're going to use it in excess. In practical terms, that means we're typically using 10 equivalents or more of that species. We'll use acetaldehyde in this case as our carbonyl compound that does have alpha hydrogens. So we're going to react that with hydroxide and water. We only have 1 enolate that we can make. We make a small amount of it. So while it could react with itself, if we have a large enough excess of benzaldehyde, it's going to react with benzaldehyde much more rapidly due to that higher concentration. So that would allow us to obtain a single aldol product, a single crossed aldol product, okay, which would look like this. Are we going to be able to stop here? Think about what we talked about at the end of class on Friday. Why will we not stop here? What's going to happen? Dehydration. Why is the dehydration spontaneous in this case, Sydney? Because we have the additional conjugation. Our double bond is not only going to be conjugated to the aldehyde carbonyl, it's also going to be conjugated to the benzene ring. Okay? All right, so this crossed aldol reaction works and will give us a single product because we've used one aldehyde or ketone with no alpha hydrogens, and we've used it in excess. Any questions? So a question for you. This beta hydroxyaldehyde intermediate, will it be soluble in water? Yes. Okay, I see people counting. If you're counting, you'll come up with a conclusion of yes. We have two functional groups capable of hydrogen bonding to water. We have a total of 9 carbons. And so, yes, this will dissolve in water. After we perform the dehydration, will it dissolve in water? No. So once we do the dehydration, we've eliminated out one of our 2 functional groups that can hydrogen bond to water. And so this would precipitate out of the solution. I was actually going to perform a very similar reaction to this. We were going to use acetone as opposed to acetaldehyde, but it was going to do the same thing. When it made it to the final product, that final product was going to precipitate out of the solution. Unfortunately, the fume hoods in the building are not working today, which meant that the lecture prep personnel, for safety reasons, were not allowed to prepare the demo. So you have to settle for me describing it to you. Which is that as we would perform this reaction, we'd have a solution, and then as we started to make more of this insoluble product, it would first get cloudy, and then we would all of a sudden see the precipitate come out of solution. So sadly, you'll have to settle for my description of this process. It would have been fun to actually perform that aldol reaction and generate that insoluble product that would have precipitated out. Okay? Either questions about this crossed aldol? Yes, Emily. Yes, we need excess of the carbonyl compound with no alpha hydrogens to suppress the self-aldol of the other one. We need a large enough concentration of this that the small amount of enolate we make is going to react with that instead of another molecule of itself. Okay. All right, so the second type of crossed aldol reaction that is useful is when one of our compounds that we're reacting is a 1,3 dicarbonyl compound. Okay. So we'll show you an example of that. We'll start with any kind of aldehyde, it doesn't matter which one. We learned about some 1,3 dicarbonyl compounds in our last chapter, chapter 23. Diethyl malonate, or the malonic ester, is one of those 1,3 dicarbonyl compounds. We can make enolates from 1,3 dicarbonyl compounds, so they're capable of participating in aldol reactions. So if we react our 1,3 dicarbonyl, our malonic ester, with an aldehyde in the presence of ethanol, we will form a crossed aldol product that will look like this. Okay. So here's our carbon-carbon bond between the alpha carbon of our 1,3 dicarbonyl, between what was the carbonyl carbon of our aldehyde, and we're going to have spontaneous dehydration in this case. We'll mention why in a moment after we look at the mechanism here on the slide. Okay. So here we have formation of the enolate. When we expose a 1,3 dicarbonyl compound to ethoxide, do we get a small amount of the enolate, or do we get complete and quantitative formation of the enolate? Do we have an equilibrium arrow here or not? Okay, so that suggests that we get basically 100% of the enolate and none of the starting compound. Why is that? We learned about this in our last chapter. Yes, please. So aldehydes are more acidic than ketones, but this compound here actually is a diester. It's not even an aldehyde or a ketone. It's a diester, but its key feature is that it's got two carbonyls in a 1,3 relationship to each other. And that makes it much more acidic than a normal aldehyde or ketone. And why is that? Yes. Okay, so the enolate that is derived from this compound, they've only drawn the minor contributor here. But if you draw this out, you find that it has two major contributors. There's two resonance structures that have negative charges on oxygen. Okay, so with two major contributors and one minor contributor, this enolate is much more stable, and that those major contributors have conjugation in it as well. And so your enolate from a 1,3-dicarbonyl compound is significantly more stable than an enolate from a normal aldehyde or ketone. So we told you in the last chapter the pKa of diethylmalonate is between 13 and 14. So when we use ethoxide, we can completely deprotonate that. The example they've given you here is an aldehyde without alpha hydrogens. They've used benzaldehyde, but it wouldn't have to be. If you mixed an aldehyde with alpha hydrogens, such as acetaldehyde, with diethylmalonate, and you added sodium ethoxide, that sodium ethoxide would still only deprotonate the diethylmalonate because it's going to be the strongest acid. It'll be stronger by several orders of magnitude, about 5 orders of magnitude stronger of an acid. Okay? So when we use a 1,3-dicarbonyl compound with sodium ethoxide, we can generate essentially 100% of an enolate from the 1,3-dicarbonyl. So there's no base left over to react to make the enolate of our other component, even if it does have alpha hydrogens. So then they react according to the standard aldol mechanism. You protonate with your solvent. We're using ethanol as our solvent instead of water in this case, but it does the same thing as water. We protonate to get this beta hydroxy compound. It's in brackets. It's not isolated. It automatically loses water. Why? Extra conjugation. Even if we didn't have a benzene ring here, we'd still have extra conjugation because this double bond would be conjugated to 2 carbonyls instead of 1. So it doesn't matter. This could be a methyl group, an ethyl group. It could be anything. We're still going to have the spontaneous dehydration with any 1,3-dicarbonyl compound because that double bond will be conjugated now to 2 carbonyls. Okay? So this is what happens in this particular case. 1,3-dicarbonyl compounds are part of a larger group of compounds we refer to as active methylene compounds. So remember, a methylene group is a CH2. So here we have a CH2 in between 2 carbonyls. So it's much, much more acidic than a normal CH2 would be. That's why we call it an active methylene compound. It's much more acidic. And we also learned in chapter 23 that beta ketoesters react comparably, the acetoacetic ester synthesis. So we can use beta ketoesters in this. That's still a 1,3-dicarbonyl compound. But we also learned that nitriles can have a similar impact on the acidity of alpha hydrogens. So this would not be a 1,3-dicarbonyl because it only has 1 carbonyl, but we could call this an active methylene compound, and it would also participate in a crossed aldol reaction where we could make an enolate at this carbon that would react exclusively with our other aldehyde or ketone to give us products of this type. And we could even have 2 nitriles. This 1,3-nitrile dinitrile compound also could participate in this type of crossed aldol reaction. Okay? Any questions about this crossed aldol? So crossed aldol reactions are very useful because there's lots of different types of products that we can convert them into. We see here a crossed aldol with formaldehyde, one of our carbonyl compounds with no alpha hydrogen, so we would get this product. And then you see that we can convert it into a whole host of different types of compounds through reduction. If we added in the heat, we could dehydrate here, and then we could reduce or add Grignard reagents or organocuprates. So aldol reactions form carbon-carbon bonds, allowing us to make larger molecules from smaller building blocks. And then because of the two functional groups that are present in those products, the carbonyl and the alcohol, we have a whole range of reactions that we can use to transform those products into other types of compounds. So very, very useful process. Okay. All right. So there is another type of crossed aldol reaction that is useful, and we refer to it as the directed aldol. Okay. So we're going to direct the aldol reaction down a certain pathway. That's why we use this name. Okay. So first thing we're going to do is we're going to make the enolate of one of our aldehydes or ketones with LDA. So we're only going to have one of our aldehydes or ketones in solution. We're going to react it with LDA, and we're going to make the enolate. And LDA is going to give us 100% of the enolate and none of that aldehyde or ketone remaining. Okay? So then we're going to add the other aldehyde or ketone to the enolate. So because we only had one of our aldehydes or ketones in solution, when we made the enolate, we have one enolate, then we add our second aldehyde or ketone, and they react in a cross-aldol fashion, giving us a single product. So let's just take a look at an example of that. And let's take our 2-methyl cyclohexanone. We use that as our example of kinetic and thermodynamic enolates. So we react that with LDA, THF, minus 78. Because we have to use LDA in this case, we're only going to be able to make the kinetic enolate. So these directed aldol reactions only work with the kinetic enolate. So here we're going to generate the less substituted enolate. Okay. And then in our second step, we can react that with an aldehyde. We'll use acetaldehyde in this case. Our nucleophilic addition step, where our enolate adds to the carbonyl. Okay. All right, that gives us this alkoxide. And in this case, we used an aprotic solvent, so we have nothing to protonate our alkoxide, which means we need to add water in a third step. Okay. So in these directed aldol reactions, we have 3 steps. First step using LDA. Second step, we add our other aldehyde or ketone. Third step, we add water as the proton source to generate the aldol product. Okay. And if we wanted the dehydration or the elimination product, then we would add heat at the same time as adding the water to cause that elimination to occur. Okay. So any questions about this directed aldol reaction? So I have a question for you. Did we form any stereocenters in this directed aldol? And if so, how many? Yes, Brady. Okay, where? Right here. Okay. And here too, yes. As you look at it more closely, you see we formed two stereocenters in this reaction. So depending on the structures of your aldehydes or ketones, you can form one or two stereocenters in those reactions. So there's multiple products possible. In this class, this is one of the rare times we're going to ignore the stereochemistry because it's complicated since we can be forming two stereocenters. So for now, we'll just recognize that that is the case. We won't ask you to predict any major products. If you take my favorite class, my Chem 553 class, in that class, you would learn how to predict the major stereoisomer from an aldol reaction. So it can be done, but it requires a stronger foundation and knowledge of organic chemistry than we can give you in this class. Okay, so for now, just recognize, yes, we're forming stereocenters, but we're not actually going to require you to predict major products. So directed aldol reactions are used quite frequently. Here's an example. We talked about paraplanone B last semester, the sex pheromone of the female American cockroach. We talked about how when they first isolated it, they weren't sure of the stereochemistry, so they had about 4 possible stereoisomers that it could be. And they synthesized them all. And the one that got the male cockroaches of New York City very excited were the ones that this professor at Columbia University was the isomer that he knew was the natural product. But one reaction that can be used in the early stages of the synthesis of paraplanone B is this directed aldol reaction. And it's kind of a complicated example because this ketone has a double bond. And so you might wonder, where's the kinetic enolate? Where's the thermodynamic enolate? Well, the kinetic enolate, even when you have a double bond, is still going to be the one from deprotonating the alpha carbon that has the most hydrogens on it. So we have two hydrogens here, one here. So we make this enolate. They've drawn the minor contributor. You react that with this aldehyde. Now this product here should look funny to you. What did I tell you would happen to a product, an aldol product such as this? It should undergo spontaneous dehydration because that double bond is going to be conjugated to that double bond. And it will. What they're leaving out here is they used some special techniques. They didn't add water. They added an anhydride in this case, and they added it at temperatures lower than 0 degrees to be able to suppress the elimination. Right? So if they'd used water, they would have had to have a temperature above 0 degrees, and it would have eliminated. But they had a way of running this reaction at lower temperatures to suppress that dehydration. Okay, so it's kind of an anomaly example relative to what we talked about in class. If you did it the way they showed here, then indeed you would get that dehydration to happen. Okay, so we need to be able to use the directed aldol reaction in a retrosynthetic fashion, same as with the simple aldol reaction. And so this figure shows us how to do that. And we do the same thing. We take the carbonyl compound, we go to the alpha carbon that is bonded either to a carbon with an oxygen or as part of a double bond, and that's what we break. Okay, so we break this carbon-carbon bond here, this carbon-carbon bond here, and this leads us to our 2 carbonyl compounds that we could react in a directed aldol reaction. But there's one more aspect to this, and that is we have to determine which of those 2 carbonyl compounds we would make the enolate from. Now in the example on the left, part A, it's trivial because they've given us one of our 2 carbonyl compounds cannot form an enolate. So there's only one directed aldol product you could get from these 2 species, and it's the one shown here because you can only make one enolate from these 2 carbonyl compounds. But over here, we have 2 ketones. We're able to make 2 different enolates in this case. And you can react 2 ketones in a directed aldol. We can't do it in a simple aldol because in the simple aldol, we're relying on equilibrium. But these directed aldol reactions are based on kinetics, and so you can use two ketones. Plus, they dehydrated in this case anyway to make it irreversible. But the point is, if you made the enolate of the cyclohexanone as opposed to the enolate of acetone, you would not get this product. You would get a totally different constitutional isomer. Okay, and we'll draw that for you on the board. So let's say we took cyclohexanone, LDA, THF, our polar aprotic solvent, minus 78 degrees. And then in step 2, we're adding acetone. Then in step 3, we're adding base. And then we're heating it up. Actually, we're adding water, because when we add water, what happens is we protonate the alkoxide, and that forms our base, right? So we don't actually have to add hydroxide. We add water in a directed aldol, and then we add heat. That will give us a compound where we form a carbon-carbon bond between the alpha carbon of our cyclohexane, right here, and the carbonyl carbon of our acetone. That was our carbonyl carbon of our acetone. And there's our double bond that we had. Okay? So as you see, this product is not the same as that product. So when you are using a directed aldol reaction in a retrosynthetic fashion, you have to specify which of the two carbonyl compounds you're making the enolate from. If we make the enolate from cyclohexanone, we get this compound. If we make it from acetone, we get that compound. So how would you know? What you do is you recognize that you disconnect the bond between the alpha and beta carbons. The carbonyl that goes with the alpha carbon is the one that you had to make the enolate from. So this bond we disconnect. The alpha carbon is now in the acetone. You see they've helpfully drawn it for you here. That tells you that this is the compound you had to make the enolate from in order to get that. If we go down here to our alternative example, our alternative constitutional isomer, we break this bond. It's the alpha carbon of the cyclohexanone that's involved in the bond that we break in the retrosynthetic direction. So therefore, we would have had to make the enolate from cyclohexanone to make this product. Okay? Any questions about the directed aldol reaction? Okay, so we can also perform intramolecular aldol reactions if we have two carbonyls in the same molecule in certain circumstances with certain types of carbonyl compounds. Okay, so here's an example. This is a 1,4-diketone. We're going to react this compound with sodium ethoxide. We're going to use ethanol as our solvent. We're also going to add heat in this reaction. And that is going to generate a 5-membered ring with a ketone and a double bond. Okay? So we formed this carbon-carbon bond via an intramolecular aldol reaction. So let's take a look at how that happens. Here's the mechanism on the screen. It's the same mechanism that we've shown you before for aldol reactions. It's just that the enolate and the ketone are present in the same molecule. So here's our starting compound, the same one I drew on the board. We make the enolate from sodium ethoxide. Now, it would have been helpful if they would have adjusted the size of those equilibrium arrows to indicate that this process is thermodynamically unfavored. Remember, we're just going to have a small amount of this enolate and a large amount of that diketone remaining behind. But if you draw the enolate in this fashion, you see that our carbon, and they've drawn the minor contributor. It doesn't matter if it's the minor or the major contributor. but that alpha carbon is 5 carbons away from the other carbonyl carbon. So you can attack that carbon in an intramolecular nucleophilic addition step, generating a 5-membered ring. You protonate the oxygen. That gives us our ethoxide. And then our ethoxide is going to deprotonate, making our enolate. So they don't show us these 2 steps, but remember we learned those 2 steps on Friday. We make an enolate, and then that enolate eliminates out the hydroxide. That's the E1CB, or the E1 conjugate base mechanism, giving us the aldol product, the intramolecular aldol product. Okay? So when we use sodium ethoxide, do we form the kinetic or the thermodynamic enolate as the major product? Sodium ethoxide, kinetic or thermodynamic enolate? That gives the thermodynamic enolate, okay? Which enolate have they drawn here, kinetic or thermodynamic? Is this the more substituted or the less substituted enolate? It would have been helpful if they'd drawn the major contributor. They've drawn the double bond here. This is the less substituted, so they've drawn the kinetic enolate. So what's going on here? Why are they drawing the kinetic enolate when we're using conditions where the thermodynamic enolate would be the major product? Yes, Brady? Okay. So you're saying that the kinetic enolate is going to react faster in the intramolecular aldol than the thermodynamic enolate. So what you're implying, what your statement implies, is that both the kinetic and the thermodynamic enolates are present. And in fact, the thermodynamic enolate may be the major, which it is, but because it cannot form a stable ring by an intramolecular aldol, it's only the kinetic enolate that's reacting. Okay? So we can go ahead and draw the kinetic or the thermodynamic enolate. We'd be deprotonating one of these alpha hydrogens with our ethoxide. We'll draw it here like this. And of course, we're only going to have a small amount of this thermodynamic enolate present. Okay. So what size ring could we make from the thermodynamic enolate? If we had an intramolecular aldol, it would be a 3-membered ring. 3-membered rings are highly strained. That's going to be unfavorable. In contrast, as you see on the screen, the kinetic enolate is able to make a 5-membered ring. Okay, so we have an equilibrium between the kinetic and the thermodynamic enolates. So the thermodynamic enolate's in there. It's actually the major enolate, so we only have a tiny amount, a fraction of 1% of the kinetic enolate, but that's the only one that can react. And then when we do this irreversible dehydration, we then use Le Chatelier's principle to funnel the reaction through that kinetic enolate. Any questions? Yes, please. In an intermolecular process? So the intramolecular process to form a 5 or a 6-membered ring is going to be more rapid than any intermolecular processes because the transition state leading to 5 and 6-membered rings don't have strain. The 6-membered ring transition states are strain-free. The 5-membered ring transition states have a very negligible amount of strain. So forming a 5 or a 6-membered ring is going to be faster than an intermolecular aldol reaction would be. So what that means is that this process is only useful for making 5 or 6-membered rings. Okay, question? Okay, so you would not make a 7-membered ring because we haven't talked about it yet, but 7-membered rings have a different type of strain in them. So once you get above 6, you get a different type of strain called transannular strain that we won't have time to talk about. But just what we need to recognize is that 7, 8, and 9, 10, those ring sizes are all strained for reasons we won't get into. So the intramolecular aldol will only work when you can form a 5 or a 6-membered ring. So with that knowledge, you should be able to get your eye clickers out and decide, go ahead and talk to your neighbors and determine what the major product will be from the intramolecular aldol reaction shown here. All right, let's get those final answers in. Okay. Keep those answers coming in. Okay, that looks like all that we have today. We'll go ahead and stop that. All right, which product do we get? What's our major product here? It is D, exactly. Okay. Could we get C as the major product? Okay, in this case, the answer is no, because this intramolecular aldol is between two ketones. Okay. And we know that aldol reactions with two ketones are not thermodynamically favored. So if we're using weak bases such as hydroxide, the equilibrium is going to favor the starting material unless you add heat to dehydrate this to get the final product. Okay, so if we leave out the heat, we wouldn't get C in this case. We would just have the starting compound. Okay. Another interesting example the book gives you of an intramolecular aldol is in the synthesis of progesterone. Progesterone is one of those female steroid sex hormones. It's the one that suppresses ovulation that is emitted during pregnancy. And you see here that there's a 6-membered ring in the product, which is a candidate to be made by an intramolecular aldol reaction. And so we use this 1,5-dicarbonyl compound. How many different enolates could we make from this 1,5-dicarbonyl compound? How many ketones do we have in this molecule? We actually have 3. We got one up here. So how many enolates could we make? We can make 1, 2, 3, 4, 5. Here there's no alpha hydrogen, so there's 5 possible enolates that can be made. How many of those enolates can cyclize to make a six-membered ring? There's just one. Technically, this one could, but it would be a bridged six-membered ring. It would be very strange because of the polycyclic ring system we already have. So there's only one of those enolates that can make a stable six-membered ring. So even though you have 5 enolates that can form, they'll be in equilibrium with each other. There's only one product that we obtain from this reaction. There's another thing you might notice here. This is a chiral ketone. We have a stereocenter here. What happens when we treat chiral ketones with alpha stereocenters with base? We learned that in chapter 23. They racemize, okay? So we can make, if we make the enolate here, we've destroyed the stereocenter. And then if we protonate that to go back to the ketone, now we could have a mixture of isomers at that carbon. But this particular ketone has many, many different stereocenters. And so we'd only be destroying one of those stereocenters. And it turns out that in this case, you would protonate faster from the back than from the front because of this methyl group you have here. And so you would get the desired diastereomer in this case. Okay, so you wouldn't have to worry. The racemization where you destroy that stereocenter usually happens when there are no other stereocenters in the molecule other than the one that's alpha to the ketone. So a lot of interesting things about this reaction. The final interesting thing is that to produce this dicarbonyl compound, they performed an ozonolysis of this cyclic alkene. Remember, we learned last semester that when we perform an ozonolysis reaction on a cyclic alkene, we get a dicarbonyl compound. So a good way to generate those dicarbonyl compounds for the intramolecular aldol is the ozonolysis of the alkene. It may seem weird to break one ring to make a new one, but it's a different kind of ring. This is a 5-membered ring. When we perform our intramolecular aldol, this methyl group now becomes part of the new ring. So we've actually expanded the ring by doing this ozonolysis ring opening, followed by an intramolecular aldol ring closing. All right, let's talk about the Claisen reaction now. The Claisen reaction is a relative of the aldol reaction that involves esters. We take 2 esters, we react them with sodium ethoxide, we get an enolate, and then we have to add acid to that enolate to get the beta ketoester. Okay? So what's happening in this reaction? Let's look at the mechanism. You'll notice I didn't draw equilibrium arrows in this case. This process is irreversible. Okay. So our ethoxide is going to deprotonate our ester to make an enolate. So we're starting out the same way we started with the aldol reaction. Is an ester more acidic or less acidic than an aldehyde? Think back to our last chapter. I'll draw the enolate that we get, and you can tell me, is an ester more acidic or less acidic than an aldehyde or ketone? It is less acidic. Why? Yeah, that ethoxide group donates to the negatively charged enolate. Okay. pKa of esters is 25. pKa of aldehydes is 17 to 18. Ketones is 19. So we have even a smaller amount of this enolate present than we would in an aldol reaction. Okay. So we're going to have just a fraction of a percent of that enolate present in solution. But when that fraction of a percent is produced, it's going to attack the carbonyl carbon of one of the remaining ester molecules. Whoops, sorry. And that's going to give us a tetrahedral intermediate. Unlike the aldol reaction, this tetrahedral intermediate has a leaving group present. It has an ethoxide group. So we can eliminate out the ethoxide group. Come over here. we have our beta ketoester, and then we've produced ethoxide. Can these two components coexist in solution? The answer is no. What happens when you have ethoxide and a beta ketoester? Deprotonates. It's up on, maybe we erased it. It was on a board, or maybe it was on the screen. This is a strong enough base to deprotonate our beta ketoester irreversibly to generate the enolate. Okay, so we're going to produce ethanol in this case. And the enolate of our beta ketoester. So this step is irreversible. So unlike the aldol reaction, which is catalytic in base, the Claisen reaction is stoichiometric in base because we convert our ethoxide into this enolate, which is much less basic. So if we don't want the enolate, if we want the beta ketoester product, in a second step, we have to add acid to that. Aqueous acid is going to be able to protonate that enolate to give us the product. And then, of course, we would form water as a byproduct from that step. Any questions? So our Claisen reaction is a nucleophilic substitution reaction on a carbonyl carbon, whereas the aldol reaction was a nucleophilic addition. Okay, so this is nucleophilic substitution because we have a leaving group, we displace that leaving group, and of course we don't stop at this beta ketoester. That leaving group ethoxide deprotonates that, which requires that final acid-base reaction. So the last thing I'll show you today is retrosynthesis involving the Claisen reaction. Claisen reactions make beta ketoesters. So we take a beta ketoester, we go to the ketone carbonyl, and we know that the bond between the ketone carbonyl and the alpha carbon, the one that's in between the two carbonyls, is the one that is formed via the Claisen reaction. So we would need 2 molecules of this particular ester to be able to make that beta ketoester. So these R groups would have to be identical in order for that product to be made by a simple Claisen. So you might wonder, could we perform a crossed Claisen? The answer is, under certain circumstances, that's what we'll start with on Wednesday. Make sure you're ready for the quiz.